Hello again. Welcome to our second lesson on graph theory. Today we're going to be looking at Euler's theorem for graph theory. Now last time we defined a number of words and concepts for our introduction to graph theory. We were looking at paths and circuits, specifically an Euler path, which is a path that crosses every edge exactly once. An Euler path begins at one vertex and ends at a second vertex. A circuit, well, a circuit is a special type of path. We're going to keep them distinct. A circuit, again, crosses every single edge exactly once. An Euler circuit begins at one vertex and ends at the same vertex. Now, a new definition. We're going to be talking about the vertex degree and looking at how the degree impacts whether we have an Euler path, an Euler circuit, or neither of those two are possible. So the vertex is the number of edges that meet at a vertex. Excuse me, the degree of a vertex is the number of edges that meet at a vertex. So looking at our sample here, A, we have one line, one path out of A. A has degree 1. Vertex B, if I start at vertex B, I've got 1, 2, 3, 4 lines that can go into B. So vertex B has degree 4. We say that degree 1 for vertex A is an odd vertex. It is an odd number. Vertex B has degree 4. It's an even vertex. Now let's take a look at vertex E. That's the one with the loop. If we zoom in on E, I've got 1, 2, because I could go either way out of E, 3, 4, 5. Vertex E is also odd, and it's degree 5. Notice that the loop counts for 2. There's something significant about when we use those vertex degrees in helping us to identify, do we have a path, do we have an Euler circuit, or do we have neither? So let's take a look at 3 different examples. First, what are the degree of each vertex, and does that graph have a path or a circuit? Graph number 1, we've got 4 vertices. A has degree 3. Vertex B has degree 5. Vertex C has degree 3. And vertex D has also degree 3. We've seen this one before. If I start at A, I go to B, to D, back to B, to A, to C, to B, I'd be stuck, all right? Can't use that last one. But if I keep going around that idea, no matter what, I'm always going to miss something. Always going to miss at least one. Neither possible. So there's no path, there's no circuit. That second one, that's the same graph that we've been using before. Vertex A has degree 1. Vertex B has degree 4. Vertex C has degree 2. Vertex D also has degree 4. And vertex E, we just saw above, has degree 5. Now let's see if we can find a path. I'm going to start at C. If I start at C, I go to B, to D, to A, D. Ooh, thinking about this, I would have to end at A. So wherever we start, we have to end at A. So if I go from C, I'm going to make my way around, stuck there. I go to B, to D, to there, around. Ooh. See, I keep getting stuck at C. Let's try one more way. Get to A. There's a whole bunch there. So it seems like I can't start at C. What if we start at E? So I'll just get that loop out of the way. And then up to C, to B, there, D, B, back to D. Oh, we started here at E, and we ended at A. I've got a path. Now, I couldn't start at C. What if I started at D? I certainly can't go up to A, because then we'd be done. So at least with D, I know that I can go out and come back and then go up to A. So let's see about that. You go to B, back to D, over to E, to B, to C. Oh, do you see it? I can't get to D to get up to A. So there's something about, we started at E, we ended at A. Started at B, ended at A. What's significant or what's different about those two? Let's take a look at graph 3. So A, I'm writing out the letter. Vertex A has 4. Vertex B has degree 4. Vertex C has degree 4. Vertex E, D has degree 4. Vertex E has degree 4. Vertex F has degree 2. Now the very first one, everything was odd. The second one, we had 2 odds. The third one, everything is even. Let's see if we can come up with a circuit. I'm just going to go alphabetical order. A to B to C to E to B to D to E to A to C to F to D to A. Oh, That time we started at A and we ended at A. We've got a circuit. Can we start someplace else? Well, with the path we couldn't, but let's start here at F. E, B, C, A, B, D, A, E, D, F. Oh, we can start and stop at F. In a way, the circuit is kind of creating a full loop. You get on a train, you're going to travel every place, and you can get off the train. It's always going to get back to the beginning. So let's put this together. This gives us an idea for Euler's theorem for graph theory. A graph has an Euler path if there are exactly two odd vertices. Notice that the path began at one odd vertex and ended at the second odd vertex. An Euler circuit exists if there are exactly zero odd vertices, or every vertex is even. Circuit begins at any vertex and ends at the same vertex. And if the graph has more than two, then it has neither an Euler path nor an Euler circuit. From here, take a look at the following 5. Notice the degree of each of the vertices of each graph, and use that idea from Euler's theorem to determine, do we have a path, do we have a circuit, or is there neither? Good luck. See you next time.